This week we're discussing plate tectonics. Plate tectonics is the foundation of this class and really of geology. Everything we talk about, from mountain building to rock type to natural disasters like volcanoes or earthquakes, can be summarized in the context of plate tectonics. You've probably heard about this before, but in general, we're talking about dividing the Earth's surface into big, thick plates that move around and bump into each other and slide apart from each other. They change size over time. Sometimes they get bigger. Sometimes they eat each other and get smaller. This theory combines two older ideas. In the early 1900s, people described continental drift. That phrase is now kind of old-fashioned. We say plate tectonics. And if you combine that with seafloor spreading, we get a big universal theory in geology. Here are the plates. Now, these aren't all the plates. These are the big players. Every red line is a boundary that shows the difference between two plates. Now, you might notice that North American plate ducks in right here. Where my cursor is, Baja California and Southern California are technically on the Pacific plate. So if anyone ever asks you what plate you live on the Pacific plate. Everything that happens on a red line is the kind of thing that might make the news. A volcanic eruption, an earthquake, a tsunami. The middle of the plate doesn't have a lot of activity. There are some exceptions we'll talk about. In general, the top of the crust is called the lithosphere. Litho means rock. It slides around on a slippery layer called the asthenosphere. Astheno means to flow. This is an easier way to think about it. The outermost part of the Earth is the crust. Beneath that, we have the mantle. By the way, the mantle is solid. In fact, every layer of the Earth, I'm not talking about the ocean, which is on the Earth, but every layer of the rocky Earth is solid except for the outer core. The lithosphere is the crust and just the top of the mantle. Makes these big crusty plates that slide around. The first person to come up with this was Alfred Wegener. He was the first scientist, at least in the northern hemisphere, to say maybe the continents are moving around. And he didn't know why, so he said something fancy and confusing. Sometimes scientists hide behind big words. When Alfred Wegener said a combination of centrifugal and gravitational force caused continental drift, that means he didn't know what was causing it. In his idea, the crust moved around, and the ocean crust was like a stationary thing. We now know that oceanic and continental crust move. Wegener was a very good thinker, even if he didn't understand the mechanism, and with a map and a pair of scissors, he was able to reconstruct continental arrangements from the past. Sometimes in Earth history, all of the continents stick together in one supercontinent. Pangaea is not the only supercontinent Earth has known. It is the most recent, and by recent, I mean a long time ago, 225 million years ago. How did he stick all these continents together to form Pangaea, which, by the way, means all lands? Well, he looked at fossils, he looked at climate clues, and he looked at the distribution of glaciers. Also, if you've ever put a jigsaw puzzle together, you know that some pieces just look like they fit. Those gave him clues. Here's a reconstruction of Pangaea. North America, South America, Africa tucked in right here. Now this might look funny to you, but if you ever go to the Appalachian Mountains in the east coast of North America, The rocks there match the Atlas Mountains in North Africa. They are the same age and the same ingredients. And these two match up with some mountains called the Hebrides, which are in Scotland. They all were touching. Once again, evidence used to reconstruct Pangaea included the jigsaw puzzle fit, fossils, and paleoclimatology. Fancy, fancy, fancy. All this means is old climate. Here's a diagram of Africa and South America, fitting together like puzzle pieces. These stripes show where you can dig up fossils, the same fossils. For example, in Triassic-aged rocks of Africa and South America, if you dig in them, you can find Cynogathus. This is a really long 9 feet or 3 meters reptile that was walking around. I mentioned that plate tectonics combine two older ideas, continental drift and seafloor spreading. If Wegener came up with continental drift, then we have to credit Harry Hess with seafloor spreading. In World War II, he made maps of the Pacific Ocean floor. Now, he was looking for enemies. He was looking for submarines of somebody that might try to sink his boat. But he accidentally did some pretty cool oceanography. In fact, he found mountains on the bottom of the ocean that were longer than any mountains on the continents. At a mid-ocean ridge, and I'll show you a picture of one in just a moment, we make new crust. This is a crust factory. Now, these ridges, these mountains, have a big valley at the top, and they have earthquakes right at the surface. They are hot, and they have lava coming out of them. By the way, this theory was proposed by Hess long before we had camera footage of a mid-ocean ridge in process. And in the late 70s, scientists went down, filmed a mid-ocean ridge, saw volcanic eruptions, and it looked exactly like Hess had predicted. It's pretty rare in science to get that sort of confirmation. It was an exciting moment. Not only did they prove the geologic theory, they found animals. We didn't know that life could exist so far from the sun and in such high heat environments. This is a cross-section of a mid-ocean ridge. Notice the rift in the middle. The volcanic rocks, they're calling them pillow basalts because they're round. And what else do we have? We have a magma chamber. I'm going to skip that. I wanted to show you a picture of one of these vents. This obviously is not smoke, it's underwater, but we do call these black smokers because it looks like chimney smoke. It's actually superheated water that has very expensive minerals in it. And the reason it's so dark is because of manganese and other minerals. By the way, this stuff could make you very rich if you could collect it. However, you would spend so much money building a submarine to take you to the bottom of the ocean that by the time you recovered these expensive minerals and metals, you would have spent more money than you could earn. However, someday, some greedy person will figure this out. I mentioned weird animals. This is the Yeti crab, and it's very fancy, wearing a little fur coat. Actually, that's not fur, but it does look like fur to me. This guy represents an ecosystem at the bottom of the ocean that nobody knew was there. People that look for life on Mars are now studying Earth's mid-ocean ridges because anything that could live in a superheated, high-pressure environment with no light might give us clues about what types of life to look for on other planets. How does seafloor spreading work? There are two theories, ridge push and slab pull. Both of them depend on heat moving around in the layer below the crust called the mantle. Ridge push is not as popular today. You will not need to know this for the exam. Slab pull, on the other hand, is reasonable. This one is caused by gravity. So the mid-ocean ridge in the middle of the ocean is where crust develops. But as the seafloor moves toward land, it eventually subducts at a different type of plate boundary we'll discuss later, and it slides under down to the lower mantle. It is recycled. Creation, destruction. Creation, destruction. The subduction here, the pulling of this crust, is what causes the mid-ocean ridge here to make new crust. Now, Vine and Matthews are two scientists that realized we could use the seafloor as a clock. Since crust is created here, torn in two, and moves half of it this way, half of it that way, it basically generates a barcode. You can sample the crust, date a mineral in it, figure out how far it has moved, and boom, you know how fast plate tectonics happens. This stands for with respect to mid-ocean ridges. What we now know is that crust moves at 1 to 6 centimeters per year. Basically, it's growing at the same rate that your fingernails are growing. Pretty slow for people, pretty fast for rocks. Another anomaly I'll talk about here is a mantle plume. Keep in mind, this is something that does not fit in with the plate tectonics model, specifically because it happens in the middle of a plate, not at those red lines I showed you earlier where plate boundaries are. For some reason, there are superheated places in the mantle all over the earth. There must be at least a dozen at any one time. And right in the middle of a plate, they make volcanoes. You may have heard of Yellowstone. You may have heard of Hawaii. These are both volcanoes formed above mantle plumes, not at a plate boundary. By the way, we don't understand these. These question marks here really indicate that scientists argue over how deep these plumes are generating from. Here's an example. The mantle plume here doesn't move, but the crust slides over it. When Kauai was over here, it formed a volcano. Then it slid off and Oahu formed. Then Maui. Now the Big Island is the only active volcano in the Hawaiian chain. All the other islands have since retired. They do not have active volcanism. Now, if you get a hot spot under a continent, it doesn't make a pretty island chain. It makes a life-killing mega disaster. And the Yellowstone caldera, at over 40 miles across, could easily wipe out, a great deal of life. This is a super volcano. It doesn't even make a mountain. It makes a giant hole in the earth, and if this erupts, you would hear about it. Some people think that when you have a mantle plume, it actually might start a new boundary. Right here, these 3 branches, they represent where a new mantle plume is forming, and these will all be baby oceans one day. Now, obviously, you're not necessarily working at a table. You might be sitting in your bed watching this. What I would like you to think about is how the idea of plate tectonics was developed. Who came up with it? What are their last names? And then in the next lesson, we will talk about another type of plate boundary.